Hello students, this is a new discussion on kinematics and theory of machines. The subject code is PCME 503 and today we are going to discuss about the introduction part of velocity in mechanisms. As you know that it is very important and a bit complicated for you people, that I know, but stay tuned, we'll discuss elaborately about it. Now regarding velocity analysis, the overview of the methods, if we think, then we get that the velocity is rate of change of position with respect to time. The graphical methods that we know are relative velocity methods and instantaneous center method. And in vector loop method, that we'll discuss in some future class. Today we are going to discuss about a part of the relative velocity method in which we know that the velocity of any point or a link with respect to another point on the same link is always perpendicular to the line of joining these points on the configuration or space diagram. As you can see in the given diagram, that one object which is irregular in shape in the left hand side, which is having a point A around which it is turning in the clockwise direction or in right hand side with respect to you people, at point B, then the velocity component which is acting perpendicular to the line which is joining AB, because it is rotating with angular velocity omega, that is called as velocity of B with respect to A, or velocity BA. Now over here, a point, third point, that is point C, which is present. Have you seen it? Between A and B? It is not exactly at the middle. It is at a distance between A to B. Now, in the vector diagram of the velocity component, the ratio at which it is at a distance of A or at a distance of B, it should be in the same ratio on the velocity component. What I mean to say, that is the physical distance of AC is to AB, that should be the similar type of velocity ratio of AB is to AC on the vector diagram. The next thing, that is the velocity analysis in relative velocity method, there are some particular criteria or analogy. Number one, that is take some convenient point O, known as the pole, in the second diagram or velocity diagram, that is in figure B. Now through O, draw OA parallel and equal to VA. Right now you are going to draw a line parallel and equal to VA to some suitable scale. Then through point A, draw a line perpendicular to capital AB. Capital AB is the actual length of the link. So what you are doing, that is through point A, draw a line perpendicular to AB. This line will represent the velocity of B with respect to A, that is VBA, as we have already discussed in the previous slide. Now through O, draw a line parallel to VB, intersecting the line of VBA at point D. Now measure OB, which gives the required velocity of point B or VB to the scale. Understood or not understood? If you have not understood, then please repeat this particular slide once again. It will be easier for you to understand this. Next, for velocity analysis, the velocity difference, that is 2 points on the same body, that we are going to discuss about. Over here, just have a look on this particular link AP. Have you noticed? This AP, it is making an angle of theta with respect to the x-axis or the horizontal axis. Now, it is rotating in clockwise direction or in the right hand side with angular velocity omega. So omega, which is having a positive value when it is turning in the left hand side and a negative value when it is turning in the right hand or clockwise direction. Now over here we have to understand that velocity of P is not the same that of velocity of P with respect to A. That is, Vp is not exactly same as of Vpa. Have you seen what is Vp and have you seen what is Vpa? Now over here it is a slider at point A. The slider is supported on the flat link which is shown in terms of a hatched line, and it is rectangular in shape. So the rectangular shaped slider, when it is moving in the right hand direction in a straight line path, its velocity component is shown by Va. So during this operation, because it is having some movement, the individual or all alone velocity component of point P is Vp. But when we are getting the turning component, that is Vp with reference to A, the velocity Vpa actually we are getting, and it is making a right angle or perpendicular or 90 degree of the link which is connecting A to P, that is capital A to capital P. Therefore, according to the vector rule, velocity P with reference to A, that is Vpa, that is equal to Vp minus Va, or Vp equal to Va plus Vpa. The diagram also is shown over here. Now case 1, that is 2 points in the same body, that is velocity difference, and case 2, 2 points in the different body, that is called as the relative velocity. Therefore Vpa, that is nothing but the difference between velocity of P and velocity of A, that is Vp minus Va. The next thing, that is velocity analysis, relative velocity of 2 points in the different bodies. So here we are seeing 2 different bodies, that is P on a particular body and A on some other particular body. So in the same method we can analyze the thing and we can find out that is Vpa as the relative velocity is the resultant, and which is not perpendicular to the line of joining the particular line between A and P. Now over here I can show you an animation to elaborate the function of a basic 4-bar mechanism. Here the gray dotted line, horizontal gray dotted line, is indicating the link 1, that is called as fixed link. The red one, you consider that it is a crank. The blue one, you consider that is a connecting rod, and the green one, you consider that is some other link. We may consider that as some third link. Okay. Sometimes we have got some particular name like rocker arm. So over here, if we start the video, we are getting that it is slowly moving in clockwise direction, and see the movement. We repeat the video. So over here all are very much connected, all are moving except the first link, that is the horizontal link. So velocity vector of a 4-bar mechanism, if you are going to analyze, then over here we see that AB, that is the first one, which is called as the crank, it is turning in the clockwise direction with omega 1 angular velocity. So at any instant we are getting the velocity component of B, Vba, it is making an angle of 90 degree or perpendicular to the imaginary line which are connecting point A to point B. So that here the AB is the crank, BC is the connecting rod, CD is the rocker arm, and DA is the fixed link. Now AB rotates with omega 1 angular velocity, as I told, clockwise direction at any instance. Now crank AB, the end A is fixed and the B rotating in clockwise direction. So the tangential velocity component Vba acts perpendicular to the link AB as shown in the figure. Accordingly, the direction of rotation of link BC in anti-clockwise direction. This is the point that you must understand, that when this type of mechanism will come into the picture, then for the adjacent links that we are considering, if the inscribed angle is less than 180 degree, I repeat, if the inscribed angle is less than 180 degree, then of course when one particular link is making a clockwise rotation, then the adjacent one, the moving one, that should make the opposite, that is anti-clockwise rotation. That happens due to its own inertia. The direction of rotation of link BC is in the anti-clockwise direction for the inertia of the component. Here the center of rotation for the case of BC, the joint end B should be considered as fixed, and the joint end C, that should be considered as a moving or rotary part which is having a tendency to rotate in the anti-clockwise direction. Now here we find that the tangential velocity component VCB acts perpendicular to the link BC as shown in figure with angular velocity omega 2. Finally, we get that the link CD rotates in the clockwise direction with VCD acting perpendicular to link CD, and obviously the angular velocity omega 3 that we have to consider. How about the introduction part? Maybe in the next video we'll discuss about the elaborate method of analyzing the velocity vector for a 4-bar mechanism, and we'll try to solve some simple numerical problems. Till then, goodbye, and thank you for all for observing and seeing this video. Have a nice day.